Okay, example 3. This is a little bit different because of the way that this paraboloid is oriented. We want to find the flux of our force, which is given by yj minus zk, where s consists of the paraboloid y equals x squared plus z squared, and that y goes from 0 to 1, and the disk x squared plus z squared is less than or equal to 1, where y equals 1. So let's take a look at what that looks like. So we are talking about the paraboloid, which is, let's see, so this one is actually centered or revolves around the y-axis because it's got x squared and z squared. So it's coming away from here like this. And then it also says it is bound by the disk x squared plus z squared is less than or equal to 1, where y equals 1. So basically, it does something like that. Okay, and that's where y equals 1 with a radius of 1, x squared plus z squared. That's this disk on the side here. So what we have, and it doesn't say this, and we're going to correct this real quick here because I didn't type it, was that this is, first of all, it's outwardly oriented. We want it to be outwardly oriented. And this is always going to be the case when you have a closed surface, which is what we have. We have the paraboloid, which is also enclosed by the disk. So this is also a closed surface. This is actually going to become an important topic in the last couple of sections, having a closed surface. It'll actually make all this a lot easier, but in this case, we're still going to do it. The way we are in this section. So what we have is we have two surfaces. We've got the surface which is part of the paraboloid, and we've got the surface which is part of the disk. And what we want to do is we want to find the flux. Again, it's what is in this outwardly oriented. What is this force field doing as it's exiting this surface, as it's coming out of the surface? So if we're looking at the paraboloid portion of this thing, again, you've got forces which are doing whatever they're doing on the inside, but as it hits the outside, we want the forces to be perpendicular to the surface, right? Normal to the surface. So all of these things, to be outwardly oriented, need to be perpendicular to the surface, because we've got this force, which is doing whatever it's doing. It's moving in all different directions in any way outside of this thing. That's what your force is doing. And then you've got stuff which is going on inside. Maybe it's going this way and then this way and then this way. It's doing a whole bunch of stuff on the inside of the surface. I'm going to erase those last few. But what we're interested in is what is happening as it's coming out. So we've got the two parts. The paraboloid portion, we want it to be perpendicular to the surface. So as you can notice here, what we're looking for is something which has a, because it doesn't matter if it's going up or not in this case, we want something which is going in the negative y direction. So that's what we're specifically looking for. So for the one that I just did for the paraboloid portion, we want to have a negative y direction, or a negative j value. Okay, and then we've got the portion which is coming out from the disk portion. Well, in order to be perpendicular, it has to be this way. Okay, there's really not much other choice there, because that's a flat disk which is at 1, so it's got to be coming out perpendicular in that direction. So in that case, we are looking for a positive y direction. So we're basically going to have to do two different surface integrals here to find the total flux. So let's see what we've got. Let's go ahead and set up the first one. So we're going to have to parameterize the first surface. And let's see, we're going to let x equal r cosine theta. And here we're not going to let y equal r sine theta, because this thing is actually centered around y. So the part that's making up the circle here is the x and the z components. So z is the part that's going to be r sine theta, and y here is going to equal, let's see, x squared plus y squared. Well, that's r cosine squared. I'm sorry, r squared cosine squared, r squared sine squared added together. So y is just going to be r squared. So our r for this one is going to be of r and theta. And so we're going to get r cosine theta, r squared, r sine theta. All right, that's going to be our r. So let's go ahead and find r sub r, which is going to be cosine theta 2r sine theta. Our r sub theta is going to be negative r sine theta 0 r cosine theta. And then we're going to need to cross. Remember what we're looking for here, because this is the paraboloid portion, we are looking for a negative y value. So let's hope that we do this correctly, and if not, we'll just switch the order of the cross and then we'll get the right one. So if we cross these things, let's see, eliminating the I row and column, we're going to get 2r squared cosine minus 0. So 2r squared cosine theta. The y part, and this is going to be the important one, if we eliminate the j row and column, we get r cosine squared minus minus or plus r sine squared. And remember that r cosine squared plus r sine squared is just going to be r, but we do have to change the sign, so we're going to get negative r. That's good. That's what we were looking for. So we're parameterizing the correct direction. And then we'll eliminate the k row and column. We get 0 minus minus or plus 2r squared sine theta. All right, so our cross is good. Okay, we're going to need to parameterize our F, our force. So the force looks like it's going to be parameterized. There is no x component, so that's 0. Then it's y, which is r squared, and then it's negative z, so that's negative r sine theta. All right, let's go ahead and dot those two things. So F dot n, remember this is n, is going to be 0 minus r cubed minus 2r cubed sine squared theta. Yeah, that looks right. So it looks like I can factor a negative r cubed out of that. So we're going to get negative r cubed and then 1 plus 2 sine squared theta. All right, that is our f dot n. So now let's go ahead and set this up in our integral. So we're going to have double integral. Let's see, we're talking about r's and thetas. Well, r has to go from 0 to 1. Theta has to go from 0 to 2 pi of negative r cubed 1 plus 2 sine squared theta dr d theta. All right, so we can separate this. So we're going to have the integral from 0 to 2 pi of 1 plus 2 sine squared theta d theta times the integral from 0 to 1 of negative r cubed dr. Unfortunately, the 2 theta part is not just going to be 2 pi in this case. We actually have something we have to integrate. All right. All right, so we've got 1 plus 2 sine squared of theta. Not something that I necessarily expect everybody to remember here, but we can go ahead and reduce this to 1 plus, now remember the reduction formula for sine squared is 1/2, so that's going to make the 2 go away, of 1 minus cosine of 2 theta d theta. And let's go ahead and take the antiderivative here of r, since we can do that pretty quickly. Okay, let's go ahead and we're going to combine the 1 plus the 1 here and make that 2 when we take the antiderivative. So we get 2 theta. Antiderivative of negative cosine of 2 theta is going to be minus 1/2 sine of 2 theta. All of that from 0 to 2 pi. And then over here we're going to get negative 1/4 minus, plugging in 0 gives us nothing. So it looks like we're going to get, let's see, if we plug in 2 pi into the first one over here, we're going to get 4 pi minus 0 minus 0 minus 0 times negative 1/4. So it looks like I get 4 pi times negative 1/4, which is just going to be negative pi. So that's the portion which is coming out of the paraboloid. Now we have to go back and do the disk. This one will be much shorter, fortunately. So let's go ahead and parameterize the disk. So this we'll call surface 2. This is the disk portion. So x is going to equal r cosine theta. Once again, z is going to equal the r sine theta part. In this case, y is just 1. It's constant, because it says it right here. That's where y is. It's just a flat disk at y equals 1. So our r is going to be, once again, of r and theta is r cosine theta 1 r sine theta. So let's do our cross product. R sub r is going to be negative r sine theta 0 r, I'm sorry, I was actually doing that with respect to something else. Whoops. So r sub r is going to be cosine theta 0 sine theta. R sub theta is going to be negative r sine theta 0 r cosine theta. All right, so crossing these, r cross r theta, eliminating the I row and column gives us 0. Awesome. Eliminating the j row and column is going to give us something, but remember the j part's where we need this to be positive now. So let's see, we get r cosine squared minus or plus r sine squared. So that's going to be, let's see, did I do that right? R squared plus r sine squared, so that should be minus r, if I'm not mistaken. And then the last one for the k is going to be 0 minus 0. So this is backwards. This actually didn't work. So this is the perfect case where what I wrote doesn't actually work. So our cross product is wrong. We really need r theta cross r sub r. Now, again, if you realize that what you've done is you've created a normal vector, well, this just means now the normal vector goes in the opposite direction. So really what we're interested in is this one. Nothing else will change, but it would have changed all the signs. So my cross product was backwards in this case, so I fixed it just by reversing the cross. All right, so now let's go ahead and, again, so we have our f. F should be, let's see, f parameterized with our given parameters here should be, let's see, there was no x. Y now is 1. And z is r, it should be negative r sine theta. So if I do n dot f, or f dot n, I'm going to get 0 plus r plus 0. Wonderful. So we just get r. All right, so this should be pretty easy to integrate. Theta, let's go red. Theta still has to go from 0 to 2 pi. R goes from 0 to 1. Our dot product is just r. And don't forget, it's dr d theta. So we get the integral from 0 to 2 pi of d theta, integral from 0 to 1 of r dr. We know the integral from 0 to 2 pi of d theta is 2 pi. Integral from 0 to 1 of r is going to be 1/2 r squared from 0 to 1. So we get 2 pi times, plugging in 1 I get a half, plugging in 0 I get 0. So we get half of 2 pi, which is pi. So our total flux is negative pi plus pi, or 0. So basically what that's saying is, however this force field is acting on this particular paraboloid, the net coming outwards is 0. There is a net flow of 0 coming out of this thing. Okay, last example, number 4. Not an extremely difficult example, just a little bit lengthy. It says that when we want to find the flux of f of x, y, z given by xi plus 2yj plus 3zk, where s is oriented outward and it's the cube with vertices at positive and negative 1 for x, y, and z. So basically we've got a cube and we want an outward orientation, which means we have 6 total surfaces that we're going to have to deal with. So let me see if I can sketch a cube here. And then the hardest part of this, is going to be something like that. Hardest part is going to be drawing the axes in the right place. So the x has to go right through here, and then got to come out this way on the y, and then be somewhere like that in the z. Supposed to be kind of right in the middle there. Did my best, I think, that I can do there. Alright, so here's what we've got. Obviously it's a cube. You've got 6 different faces. So we're going to have 6 surfaces that we have to deal with here. So we're going to call the one that's over here on this side, facing us, the closest one to us, we're going to call that S sub 1. And hopefully what you see is that there's going to be a pattern here that develops, and if you can recognize the pattern, that's going to be make things a lot easier. So if we want this to be outwardly oriented, the flux of this to be outwardly oriented, which means we want everything to be coming perpendicular to S sub 1, so we want everything coming straight off of here parallel to the x-axis. Again, those are perpendicular, remember, coming out of there. Those are all going to be perpendicular. So we want everything to be parallel to the x-axis, and on surface 1, we want this to have a positive I component. We want the I part to be positive. So let's go ahead and parameterize surface 1, and again, hopefully you'll start to see the pattern. We won't have to do every single surface the same way. Well, let's see. So in the first surface here, x is 1. Because that's where this is. All these values right here are 1. X is 1, so we can just call y, y, and z, z. So our r is going to be r of yz, which is going to be 1, y, z. So we're going to have to do r sub y, which is going to be 0, 1, 0, r sub z, which is going to be 0, 0, 1, and hopefully you'll see that these are going to be really easy to deal with. We're going to need the cross product, and remember, we want the cross of this to have a positive x value, so let's hope that this works out. So ry cross rz, eliminating the I row and column is just going to give us 1, minus 0 is 1, so we're already good there. Eliminating the j row and column is going to give us 0, eliminating the k row and column is going to give us 0. And again, you can check those real quick, but that's going to be your cross product. We do need the function parameterized. Okay, so the function parameterized is going to be, let's see, x is 1, y is y, so we're going to get 2y, and z is z, so we're going to get 3z. And the good thing is, here you can see if you take your n and you dot it with f, well, the y and z components go away. So f dot n is just 1. So if I were to take the double integral, let me scroll this up just a little bit here. If I was to take the double integral over d of 1 dA, well, that's just going to be the integral from -1 to 1, integral from -1 to 1 of 1 dy dz, because y and z both go from -1 to 1. Well, the integral from -1 to 1 of dy and the integral from -1 to 1 of dz are both just 2. So here we're just going to get 2 times 2, which is 4. So that's the flux coming out of the positive z-axis. So now we need to do S sub 2. We're going to call S sub 2 the backside of the cube. So I don't know how best to describe that. We'll write it up there. That looks maybe like it's pointing to the backside of the cube. Well, it's going to be exactly the same thing, except that this time we want there to be a negative I component because it's going in the negative x direction when it flows out the back. So that's what we're looking for there. So we want our normal vector, when we do everything, our normal vector should be -1, 0, 0. So do we have to go through the entire cross product process? No, not really. We know that our normal vector has to be -1, 0, 0. Okay, I do need to at least put in f. F in this case, now remember it's going to be exactly the same, except that the x part would be -1. So we're going to get -1, 2y, 3z. That would be f parameterized. And again, that's only because the x, in this case, I didn't write it down, but the x would be parameterized as -1 since it's on the back side of the cube. So when we dot f and n, here we're just going to get 1 again. Well, we've already done the double integral. It's exactly the same thing. So the double integral over d of 1 dA is just going to end up being 2 times 2 again, which is 4. All right? So that's the first two components. So as you can see, we didn't have to necessarily write everything out. Let's go ahead and talk about S sub 3. And we'll call S sub 3 this piece right here, kind of the right side of the cube as we're looking at it. So S sub 3, so if we want everything coming out of S sub 3 with a positive orientation, that means it has to have a positive j component. It's got to have a positive j component. So we already know that, I mean, we're going to write it down anyway here. X is going to be x, y is going to be 1 because that's a flat y value, and z is going to be z. So r of x is supposed to be x. R of x and z is going to be x 1 z. And then r sub x is going to be 1 0 0. R sub z is going to be 0 0 1. I have no idea what that piece was there. So if I cross Rx and Rz, let's see, we get, if I eliminate I row and column, 0 minus 0. The j part, we're going to get 1, but we have to change the sign. That's -1, so I actually have this backwards, which is okay. We'll fix it. And then 0 for my last component there. So we really needed to have r sub z cross r sub x, which is going to give us 0 1 0. Now I didn't really have to go through that entire process. We should have already known that 0 1 0 is the only way you're going to get a perpendicular vector to the surface S sub 3. But I do need to go ahead and parameterize f. Okay, and the function f was x, 2y, 3z. So x, in this case, is x. 2y is just 2. And then 3z is our z component. So let's go ahead and dot these. Well, again, if I dot anything with the x or the z component, there's 0 because the cross product, which was the normal vector, has 0 in the x and z component. So all I get out of the dot product of f and n here is 2. So I'm going to go ahead and take the double integral over d of 2. dA. But remember, each one of these bounds goes from -1 to 1. So that 2 could technically be pulled out as a constant. So I had 2 times the double integral of 1 dA. We've already done this one twice. That gave us 4. So what we get is 2 times 4, which is 8. Okay, and I apologize. This is going all over the place here. S sub 4, well, we're going to call S sub 4 the other side from S sub 3. So that'll be like this side right here. That'll be S sub 4. So the only thing that changes there now is that the y value is -1. So with S sub 4, we just need there to be a negative j component. So we know our normal vector. I'm not going to go through the entire process, but we know the normal vector has to be 0, -1, 0. So if we do f dotted with n, now remember in this case the only difference here now is that the y component is negative, so f is going to be x -2, 3z. F dotted with n, that is going to give me 0 plus 2 plus 0, so we get 2. It's going to give us exactly the same thing. Of 2 dA, we just did that, is also going to be 8. All right. S sub 4 and S sub 5 and S sub 6 are going to be done the same way. S sub 5 and S sub 6 we're going to kind of combine, and we're going to show it's going to be done the same way. So S sub 5 we'll call the bottom, I guess, and then S sub 6 we'll call the top of this thing. All right. So we know, now we are going to take some shortcuts on this one. We know that the normal vector, if we do S sub 5, the z component needs to be negative. It needs to be going down. So the normal vector is going to be 0, 0, -1. F, parameterized, well again, z is -1. Does it really matter what the x and y are here? Not really, because when I dot them, it's going to be multiplied by 0. So I do know that my z component is -1. So let's see, that was negative, so it's going to be 3 times -1, or -3. So f dotted with n is going to be 3. So my double integral over d of 3 dA is like pulling a 3 out to the front and then having the double integral over d, double integral over d of 1 dA. So really what we get is 3 times 4, or 12. And you're going to get exactly the same thing when you do S sub 6. The only difference is the normal vector is going to be +1, and your z component is going to be +3 in your force. So you're going to get exactly the same thing. So you're also going to get 12 for that one. So what we ultimately get is 4 plus 4 plus 8 plus 8 plus 12 plus 12, or what is that, 24, 16, 48. So you get a flux of 48. This is actually going to be something that will be made much easier when we get to 16.9, but for right now, that is how you would do the surface integral of the flux of that cube.